Electrochemical dimensional processing has opened up new technological opportunities in modern mechanical engineering and contributes to the successful development of a number of industries. Electrochemical methods of processing metals and alloys based on the process of anodic dissolution during electrolysis. A current is passed through the electrolyte, oxidation and reduction reactions take place on the electrodes. The anode, it is located on the left, dissolves. The dissolution products precipitate, gas is released at the cathode. On the quantitative side, these processes obey Faraday's law. The amount of released substance is proportional to the electrochemical equivalent and the amount of electricity passed through the solution. The electrochemical equivalent is determined by the ratio of the atomic weight of a substance to its valence and Faraday number. The Faraday number is a constant. To account for the effect of adverse reactions, the concept of flow output is introduced. The output to the flow shows how much of the past electricity is spent on the main dissolution reaction. This value is determined by the ratio of the amount of practically dissolved substance to the calculated one. Consider the behavior of a metal in a solution of its salt. The copper electrode is lowered into a solution of copper sulfate. When a metal comes into contact, on the screen it is on the left, with a liquid, a potential jump occurs at the phase boundary. The potential difference between a metal and its salt solution is called the electrode potential. The charges form a so-called double electric layer at the phase boundary. Its thickness is about 10 microns. An excess of electrons accumulates on the electrode, it acquires a negative charge. Positive ions are located in the electrolyte at a distance of the ionic radius. The potential of the double layer varies with distance almost linearly. If the potential of the electrode is increased with the help of an external source, the ion energy in the metal will increase, the equilibrium state is disturbed. The rate of ion release from the metal into the solution increases, and the rate of reverse transition decreases. An electric current flows through the electrode boundary of the electrolyte solution. The metal dissolves. An increase in the potential of the electrode over the equilibrium is called polarization. With increasing potential, the current strength increases. Along with this, the rate of dissolution also increases. If metal ions are not removed in a timely manner from the electrolyte layer adjacent to the canode, then the potential of this layer will increase. The transition of ions into the solution will slow down, the dissolution process may stop. This will not happen if the concentration of hydroxyl ions is sufficient, and as a result of interaction with metal ions, the dissolution products are converted into a precipitate. Thus, the intensity of dissolution is determined by the rate of electrochemical reaction in the double layer and the rate of diffusion processes. It follows from Faraday's law that the rate of metal dissolution is proportional to the current density of the node. However, with a significant increase in the current density in the non-flowing electrolyte, it is possible to slow down or completely stop the process. What is the reason for this phenomenon? Special filming allows you to see that the surface of the anode is covered with a layer of dissolution products. This is a passivating film. The thickness of the film is very small, but it has significant electrical resistance. The intensity of dissolution decreases sharply. The processes occurring on the node can be represented using a polarization curve. The rate of dissolution of the proportional current density increases with increasing potential. However, with increasing polarization, the density of the anode current decreases, a passivating film appears. The rate of dissolution of the metal is sharply reduced. At higher values of the anode potential, higher valence oxides are formed, which are easily removed from the metal surface. Along with this, the release of oxygen increases. There comes a so-called reshuffling. The rate of the metal dissolution reaction increases. By selecting the composition and concentration of the electrolyte solution, it is possible to achieve a reduction in passivation. The most widespread are aqueous solutions of sodium chloride. Chlorine ions activate the dissolution process. Seeding in such electrolytes almost does not occur or has a weakly pronounced character. Thus, the composition of the electrolyte has a significant impact on the performance of the process. Electrochemical treatment acquired practical significance after methods for removing dissolution products, methods for maintaining the active state of the electrode surface and localization of the process were developed. A wide variety of schemes and methods of electrochemical processing makes it possible to manufacture parts of complex shape from materials with any mechanical properties. These methods make it possible to achieve a metal removal capacity of 1,500, 1,800 cubic millimeters per minute per 1,000 amperes of operating current. The treated surface has a high purity class. Besides, there is no zone of thermal influence. A very important feature of electrochemical processing is that the dissolution rate does not depend on the mechanical properties of the part material. In an electrochemical system, the workpiece is the anode, and the tool is the cathode. The gap between them is filled with an electrolyte solution. Turn on the current. The material of the part, you see it from above, dissolves evenly. But if the part has a protrusion, metal removal proceeds more intensively on the protruding part, where the interelectrode gap is smaller. With the help of a special integrator, you can see how the electric field is distributed. In the interelectrode gap, Usually the gap between the electrodes is 0.05 of a millimeter. The smaller the gap, the higher the processing performance and accuracy. This property is used to localize the treatment by choosing the appropriate shape and size of the electrodes. The process can also be localized by applying an electrical insulating layer to non-working areas of the tool or part. Processing with high productivity cannot be carried out without effective removal of dissolution products from the inter-electrode gap. The method of removing dissolution products by electrolyte flow is widely used. This treatment is called anodic hydraulic. In this case, the solution is pumped at a pressure of 10 to 20 atmospheres at a speed of 3 to 20 meters per second. Consider the dynamics of the flow in the inter-electrode gap. When the flow enters a narrow gap, the pressure drops. The action of molecular forces forms a layer of stationary molecules 3 to 7 microns thick at the surface of the electrodes. The neighboring layer is moving at a low speed. In the layers further away from the electrode, the flow rate increases. Here, at a certain flow velocity, a turbulent regime is established, which ensures the best removal of dissolution products. The process does not stop even at high current densities. If the electrolyte flow rate is insufficient, the dissolution products do not have time to be removed, concentration polarization increases, postivation and even gap breakdown may occur. An excessive increase in the flow rate significantly increases the hydraulic resistance in the gap, cavitation occurs. The ammic resistance increases, the rate of metal dissolution decreases, the purity of processing deteriorates sharply, jet irregularities and grooves form on the parts. To fill the gap evenly with the electrolyte solution and prevent the formation of gas cavities at the outlet of the system, local hydrodynamic resistance is created, which takes about half of the electrolyte pressure to overcome. In this case, the surface cleanliness and dimensional accuracy are maintained even when processing parts of complex shape. For the same purposes, compressed neutral gas is supplied to the gap along with the electrolyte. Here the electrical conductivity of the electrolyte decreases somewhat, but the viscosity of the liquid decreases and the gap filling improves. During processing, technologists usually experimentally choose hydrodynamic conditions that ensure complete evacuation of dissolution products from the gap. Another option of electrochemical treatment opens up great prospects: electroabrasive. It is based on a combined electrochemical and mechanical effect on the workpiece. The durable anode film is removed from the treated surface by abrasive grains. The instrument is a conductive active circle. Anodic mechanical processing has also become widespread. In this case, a metal disc cathode is used to remove the anode film.